Now I'd like to introduce Sean Murphy, our presenter today, presenting Unlocking Soil Water. Sean is a research officer with New South Wales DPIRD, based at the Tamworth Agricultural Institute in New South Wales. Over the past 30 years, Sean has conducted hydrology research in pasture and crop systems to develop profitable, adaptive and sustainable primary industries in New South Wales. Over to you, Sean.
Thanks, Luke, and thank you everyone for joining with us this afternoon after lunch to explore how we might unlock soil water. The catalyst for this presentation came from the National Soil Action Plan, and after some surveys and some needs analysis, it was identified that maybe there's a need to help understand and manage soil moisture better, to focus on some evidence-based tools and information that can assist all growers of crops, pastures, rain-fed and irrigated to help understand soil water. So hence, Unlocking Soil Water is the title. I think at times the world of soil water appears confusing, sometimes hidden, inaccessible, which can leave us fumbling for the right key. From another perspective, we might want to unlock more soil water from the soil, but we don't know which key to use. So this presentation aims to do two things: unlock some of the mystery around soil water, terms and definitions, but also how to approach the locks to show how we can release more soil water. The description for the webinar promised a lot, but as I went through the process of building it, it turned out that I might have overpromised just a little bit. I've pared it back to be more manageable, but we will cover a lot, so no apologies for that, because I want to cover some key concepts that help us frame how we interpret soil water and maybe how we can help unlock it. So stay with me, enjoy the ride, and as always, reach out if I can assist further. So that's an outline of where I'm going to go, but the soil water space can be challenging. It's a challenging world. So as we move through the presentation, I want you to think about a paddock where the soil is challenging you. Is it deep? Is it shallow? What is its texture? How does water get into that soil? What crops or pastures grow well on it? How could we get them to grow better? What is the primary restriction, and can we unlock it? If we have that paddock in our mind as I walk through the presentation, I think it will help to put the material into more context. So that begs the question, what is the right key for you? For some, the key is to unlock some of this terminology around soil water to help us understand what we mean when we discuss certain things. For others, it might be, well, how do I get my plant system to access more soil water? Is it even possible to do so? Hopefully, my presentation will get you thinking about what might be your lock and how best to find that right key. But first, I'll ask that question. It's a fundamental question. Why do plants need soil water? Have you actually stopped to think about that? Well, why do plants need soil water? When I've asked this question in live audiences, the answers go something like, oh, well, because, well, without water, plants won't grow, or plants wilt. And they're perfectly valid answers. But looking deeper, plants need soil water for a range of reasons. And perhaps most fundamentally, it is to facilitate the exchange of CO2 with the atmosphere. So there is a continuum of water from the soil through the plant to the atmosphere. And while ever plants maintain their turgor, they have their ability to grow. And with the right potential, they can facilitate osmotic intake and transport of valuable nutrients. How do we interpret soil water? So soil water comes in many different guises, and depending on the need, we might interpret soil water by mass, by volume, or by tension. And I'll walk through each one of these now in a little bit more detail so that we're all on the same page when we start talking about the different appearances of water in the soil. So firstly, gravimetric. Gravimetric is the most accessible way to interpret soil water. I think most people on the call today would have done this at some stage, whether as a one-off or repeated measures through time, or checking soil water before planting a crop or a pasture. However, the gravimetric moisture is somewhat meaningless. It gives us no meaningful interpretation of how our plants will perform in that soil. And an analogy might be, if you're buying a truckload of loam or compost or chicken litter, would you rather pay by cubic meter or by weight? If any of those have a high gravimetric water content and you pay by weight, you would be paying for the water. So from that point of view, it's dry weight would be a much better way to buy that material. So accessing gravimetric water content, it's easy to do by soil cores or by auger and subsample and so on. The next way to interpret soil water is by volumetric water content. Now, volumetric water content is useful because it can place soil water into a tangible value. We can relate it to the millimeters of rainfall equivalent when we integrate it with depth and area. How many millimeters of water do we have stored in the profile at any given time? Or how many megaliters of water do I need to apply to a hectare to raise the soil water content by 10%? But unfortunately, to accurately interpret volumetric water content, we need to know the bulk density of the soil, which is a challenge to most people. So some of the various devices I've used to estimate volumetric water content over the years include capacitance sensors, neutron moisture meters, EM38, and so on. But once we have an interpretation of soil water in the volumetric realm, we can really wrap our fingers around it and understand it better. And that leads us on to the third one, soil water potential. Now, this is where the rubber really hits the road in terms of relating what our plants experience when they are growing in the soil. The total soil water potential represents a combination of forces that describe how much work is required for soil water to move. Now, the plant has to fight matrix, osmotic, gravitational potential to extract water from the soil. In the field, we might be able to use soil tensiometers to gauge the water potential. In the lab, we can use various systems to estimate the water release curve for each soil. The graph at the top is a representation of soil water release curves for a range of soils. All soils and situations are unique in this capacity. A note on terminologies. In the paddock, we often hear about field capacity. Field capacity is determined as the water content a day or two after saturation and free drainage has taken place. Now, depending on the soil texture and the hydraulic conductivity of the soil, it could be sooner or later than a day or two. On the other hand, people would have heard wilting point, and that occurs when plants can no longer maintain their turgor in order to extract water from the soil. Soil texture. What is the importance of soil texture? Soil texture is one of the primary things that determines how much water a soil can hold and how much of that water might be accessible to our plants. And the texture triangle is how we determine what the soil texture is. So all soils are made up of clay, silt, and sand, and their relative proportions determine the texture. So a silty clay loam might be 30% clay with 30% silt and 40% sand, and where the lines intersect tell us that it's a silty clay loam. Now, particle size of those different components is also critically important. So this graphic illustrates the relative sizes of the different soil particles. At first glance, it looks a little bit like a diagram of the solar system, with the sun over on the left and Pluto, that little dot over on the right. But it's the relative sizes of the particles in our soil. The finer the matrix with silt and clay particles, the greater the pore volume, assuming that soil structure is stable. A soil with coarse sand particles and gravel will have good storage volume, but the pores will be larger, meaning the soil water will drain freely and more quickly. Another critical aspect of the soil is bulk density. So soil structure and density are critical to the absolute maximum amount of water that can be stored in the soil. To store more water, you need to improve the structure and the pore space volume. Now, things like organic matter leading to water-stable aggregates, well, they help maintain that structure. If there are soil chemical constraints, like sodicity, then clay particles will be mobile and they can lead to clogging of pore space, reducing the total storage and conductivity. In the table here, we see sandy loam, loam, silt clay, and clay with a bulk density determined, which tells us the absolute pore space volume that would be available in that soil. Now, because that first one says 40% pore space volume, it doesn't mean that all of that pore space can be occupied by water. Some of it can never be filled because they're tiny little pockets in the soil where the water just physically can't get to. So there is an adjustment to determine the total amount of volume that can be occupied by water. But how much water can a soil hold? So these bars show a range of soil textures along the bottom, sand, sandy loam, loam, etc., through to self-mulching clay. And the y-axis represents the amount of water that can be stored in them per metre of soil depth. Now, the black area is the proportion of total storage that sits in the plant available range, and I'll be delving more into that later. So as you can see, for a sand on the left of the screen, it has good total storage, but most of that storage is in the free draining range. So from 400 back down to 120. That's that rapid drainage that occurs in sandy soils. Only 60 millimeters is available in the plant available range, whereas a self-mulching clay on the right-hand side has a slightly greater total storage, but a smaller proportion sits in the free drainage range and a larger proportion fits in the plant available range. But notice the large component sitting in the unavailable range below permanent wilting point. So that puts into context the relative differences of how much water can be stored in soils of different textures and how much of it might be available to the plants. Which now leads me on to, well, we've got some soils, we've got some textures, we've got different particles, we've got good structure, but how do plants access soil water? Well, now I want to enter the murky world of how plants physically access soil water. So the next section, I could spend an entire day in its own right, but it is important to be aware of, as this is what brings together why plants can or cannot access soil water in any given circumstance. You can see in the photo there that the poor old squash plants are failing to access the water they need at that time. They're wilted, they've lost their turgor. So this brings into play the soil plant atmosphere continuum, which I mentioned a little bit earlier. Now, this continuum is a gradient in water potential from the soil to the atmosphere. This gradient allows water to move through the soil, into the roots, through the xylem, up to the leaves, out through the stomata to the atmosphere. Now, water moves from a high water potential, which is less negative, to a low water potential, which is more negative. As long as the plant can maintain a more negative potential than that in the soil, water can move into the root and so on. So now you can start to appreciate one of the locks I'm trying to open here is terminology. So the terminology that exists in the soil water realm can become somewhat confusing. Water moves from a high water potential, but it's less negative, to a low water potential, but it's more negative. You can see why it's easy to get confused. So in the little example here I've got in the diagram, in the red box, we can see that the soil water potential is minus 0.3 megapascals. And in the root, it's minus 0.5 megapascals. If the water content drops in the soil so that the water potential is now minus 0.6 megapascals, and the potential in the root is still minus 0.5 megapascals, the plant cannot access the water. For each soil, the soil water release curve relates the water potential to the volumetric water content. Now, each soil has a different shape curve. They're all unique. But typically, so that we can compare one soil to another, there's a couple of parameters that we define. The first one is field capacity at around minus 33 kPa, kilopascals, and wilting point at around 1500 kPa. Now, it's important to remember that these are just nominal values. They're nominal values that are set because we can test them in the lab so that we can compare one soil to another. What a plant sees is unique to the individual plant or the plant type, which we'll explore a little bit later on. So let's walk through these graphs. So firstly, we've got three soils, a loamy fine sand, a fine sandy loam, and a silt loam. Along the x-axis is water potential, ranging from 0 up to 1 million kilopascals over on the right-hand side. The y-axis is volumetric water content, from 0 up to 55. So you can see each of the curves has a different shape, like a slippery dip. Some of us might like to go down that one, whereas a thrill seeker might like to go down that one. The horizontal blue lines on the screen are where the water potential intersects each of the curves, and we can determine the volumetric water content. So the loamy fine sand is at 5%, the fine sandy loam is at 17%, and the silt loam is at 33%. Now let's jump to wilting point. So the same graphs, but now I've intersected where wilting point is. So the loamy fine sand at 2, fine sandy loam at 5, and the silt loam at 12. Now, when we compare the two lines together, we get to see what is available to plants. So here I've marked up silty loam, and it has a plant available amount of about 21%, and the others 3 and 12%. So typically we do these studies in the lab, taking cores from the field, which is quite a time-consuming and technical process that most people don't have access to. However, if we do want to compare one soil against another in a standard manner, these are the types of measures we would take. So the plant available component here for this one, between 12 and 33%, the blue line and the red line. Now I'm going to present a slide which will make most people recoil in horror. I don't tend to present slides like this. I don't like so many words on a page, but I've done it for a reason. So you might be wondering, well, I've heard of stored soil water. I've also heard of plant available water. I've heard of available water content. I've heard of raw. Well, I've put all these on to demonstrate the range of concepts that sit behind each of these terms. Come back to this slide later, have a closer read. But I ask the question, what do I do with this alphabet soup of terms to describe soil water? Well, they each have a role in describing different circumstances, but often we do not have the data for all of these terms, so it's a matter of using the right ones for the job. Typically, in my work, I like to use SSW, or stored soil water, in millimeters, because it's tangible. It's something that we can readily communicate and discuss one situation versus another. If I was to have a discussion with you and say, oh, well, this is great, this soil's sitting at 1300 kPa and this soil over here is sitting at 200 kPa, it doesn't mean very much. But if I say to you that the first soil has 45 millimeters of available water in it, but the second soil has 145 millimeters of available water in it, now it actually means something. So it's a matter of choosing the right term for the right job. One of the terms I want to just highlight, because it's come up recently in discussions here and there, is RAW. Now, RAW, the acronym for readily available water. Now, raw, as shown on this gauge, is actually in the wetter end of the water potential range. So here is field capacity on this one, dictated about -10 kPa, and here is permanent wilting point, way over on the left at -1500 kPa. Raw, or readily available water, is this small fraction here. Why is it so small? Well, remembering our soil plant atmosphere continuum from earlier slides, plants do not have to work very hard to extract water at those potentials. So plant turgor can be fully maintained and growth can continue uninterrupted. So in an irrigation sense, where we're optimizing growth, we want to irrigate when we reach that threshold. We don't want to irrigate later because the plants would have to work harder to extract that water, which would curtail their growth. So as you can see, many different definitions, very different guises of soil water, if you like, that we use in different circumstances. Some examples from the real world, just a couple of photos from my collection. The first one I want to explore is plant available water capacity. Now, the AppSoil database has reference values for plant available water capacity, or PORC, on different crops and pastures growing on different soils around Australia. I've pulled out a couple to demonstrate the differences in what different crop types are able to extract. So here on this panel, I'm going to show a couple of these graphs. On the x-axis, we have our volumetric soil water content. And on our y-axis, this is actually soil depth. So going down in the soil profile, down to 2 meters deep. And the blue line represents the drained upper limit for the soil, let's say field capacity. And the orange and green lines represent the lower limits for the two different crops. The green one being wheat and the orange one being chickpea. So here on this soil, wheat was able to extract an additional 27 millimeters of total water from that soil compared to chickpea, resulting in a slightly higher PORC value of 219 millimeters compared with 192 for the chickpea. Let's skip to a summer crop situation. It's the same soil, but now we've changed crops to summer growing types of cotton and sorghum. So cotton was able to extract 24 millimeters of additional soil water for a total PORC value of 276 millimeters. So the cotton can extract more than sorghum, which is more than wheat, which is more than chickpea, all on the same soil. So for multiple locations around Australia using Google Earth, you can go and explore those PORC values or those capacities of different crops and pastures around Australia. Let's move to the pasture space. Here I have an example with digit grass and lucerne. So these data come from a digit lucerne density experiment, which we had growing at TAI. And it's a spaced plant experiment where all treatments had the same density of plants at 8 plants per square meter. We had a range of treatments which varied the proportions of each of them. So ranging from all digit grass to all lucerne, but with 3 intermediate treatments with densities of 25, 50 or 75% occupied by the lucerne. I wanted to explore the contrasting ends, so all digit or all lucerne. So here we have some graphs I call heat maps of water content. The x-axis represents nearly 4 years of time from 2018 to 2022. The y-axis represents soil depth, a bit like we've seen on some of the earlier graphs. And it's representing a cross-section of the soil through time. The hotter the color, the drier the soil. The upper panel is digit grass on its own, and the bottom panel is lucerne on its own. So we can see that the digit grass, in terms of interpreting volumetric soil water content, dries the soil to a greater extent in this period, but also replenishes with water infiltrating deep into the soil in this period when the better rains came along. Whereas lucerne maintained a more even water content, if you like, throughout the period. Didn't get as dry as digit grass, but also didn't allow as much infiltration as the digit grass once the rains came. So using that information, we can make some interpretations about the plant available water capacity for these two pasture types. So here we have the same graph setup as we saw for the cropping examples, and digit grass at these densities could dry the soil profile down to this depth by an additional 64 millimeters compared with lucerne. Now the difference comes from the upper 1.5 meters or so of the soil, where a greater root density and possibly digit having a lower plant water potential allowed the grass to extract more water from the soil than did lucerne. And this is resulting in a pork value for digit grass here of 302 millimeters and lucerne having 238. The next example, I wanted to really contrast different plant types. And so this experiment included lucerne, a tropical tree legume, and our digit grass, our tropical grass. And I want to explore the impact of root abundance and density on accessing soil water. So the photo on the left is lucerne growing, but as you can see around the base of the lucerne, there's no grass. The photograph on the right is the lucerne, but having digit grass all around it, underneath it and around it, which creates two different scenarios. In the middle is a photograph of a 2-meter deep trench, which we dug at the conclusion of the experiment so we could count roots. So you can see lucerne roots sticking out of the soil profile there, the large, easily visible ones, the digit grass ones much finer. So what we did was counted roots, but we also measured the soil water content from 2014 to 2018. So on the x-axis is our time from 2014 to 2018. On our left-hand vertical axis is our total stored soil water in millimeters. And on our right-hand axis is just a record of daily rainfall in the bars. So what we can see here is that the red trace, which is digit grass, dried the soil profile or maintained the soil profile at a lower level than did lucerne, which begs the question. So Sean, you're saying what? A tree legume like lucerne dried the soil less than a tropical grass? Well, yeah, in this example, digit grass has a greater pork than the lucerne for this section of the profile, 0 to 2 meters. Now, digit grass doesn't have as deep roots, but it has a greater abundance of roots, and so a greater ability to remove and access water from the upper profile. How did we know about root abundance? Well, from that trench in the photograph 2 slides before, which showed a cross-section of the soil, we counted all the roots exposed in the face of that trench and mapped them. And with digit grass in the treatment, what we saw was we had a greater abundance of roots in the upper part of the profile, the upper 1.5 meters, compared with lucerne on its own. Now, don't get me wrong, lucerne had deep roots. The photograph on the left is a close-up of lucerne roots from 2 meters deep in the profile, where you could see the roots traversing through the soil in the interfaces on the slickened side faces of the vertisol, accessing deep soil moisture. Anecdotally, during the height of the drought, when everything else was dry and crispy, lucerne was still transpiring and was still accessing water from beyond 2 meters deep. So the greater abundance of roots in that upper profile from the digit grass is what allowed it to access water in the upper profile, but deeper roots by the lucerne accessing water from beyond. If we interpret the abundance of roots here, perhaps we can ask a question: what is going on at 0.8 meters depth? Is there a soil physical constraint at that point, i.e. higher density or something like that, which is restricting the abundance of roots there? So it's an interesting way of interpreting the profile. So that's pretty much where I'm at for running you through this journey. I've shown a range of locks and a range of keys. Now I ask you which one is the right key for that paddock I asked you to think about at the beginning. Is it a better understanding of soil water interpretation, or is it identifying a key chemical constraint that prevents your plants from taking up water? Is soil structure the major constraint to maximizing total water storage? Can you change the plant type to one that has more roots or deeper roots, or can tolerate a lower plant water potential? For instance, drought-tolerant varieties that use osmotic adjustment to maintain their turgor for longer under drying conditions. An example of that is strawberry clover versus white clover, or maybe even digit grass versus lucerne, and so on. So that's the main part of my presentation. I will acknowledge the support of the National Soil Action Plan in putting this presentation together. I also acknowledge my fellow colleagues in DPIRD, Justine, Sarah and Luke, for helping tailor the direction of the presentation, and Robert Hoogers and the Waterwise for some of the illustration and resources. My contacts always come back. Feel free to engage. Happy to discuss all things soil water.